Okay, thanks a lot. So in the previous session, we talked about universality and undecidability in computation, and I tried to convey some of my fascination for these concepts for Turing machines, namely how universality appears there, and how at the same time, more or less, everything is uncomputable. And I'd like to now consider a similar question for other systems that apparently are inequivalent or are not the same. But actually, we want to understand their relation, okay? But so the first important example, which kind of got me started in all of that, are spin models. And so this story starts with a realization of that some spin models, which I'll define in a second, that appear to be simple, are in fact universal, where that means that they can simulate complicated spin models, which means that, well, that includes models with high-dimensional spins, as in not only two-level spins, or with many body interactions, like four-body interactions, as in this picture, or on high-dimensional lattices or graphs. And so all of these features can be reproduced in a certain way by some models, spin models, that appear to be simpler. And in this sense, they are called universal. And I'll spend the next like 10 to 15 minutes explaining this statement. And then I'll raise a question of what is the relation between this notion of universality and Turing machines and other notions of universality. So a classical spin model is the following. So first of all, we have a so-called spin, which is a bit of a misnomer because actually it just stands for any classical and discrete variable, like 0, 1, like a bit. And the Hamiltonian stands for either a cost function, so just a function, but it's typically called a cost function because you want to optimize it usually, or for a family of cost functions. I will distinguish these two cases in a second. Typically, they have a local structure, which should play the role of our grammar from previously. Okay, some sort of some local interactions that generate a possibly infinite set of such functions. The paradigmatic spin model is the Ising model, which is sort of defined this way. If defined on a graph G, then usually spins, which are two-level variables, are assigned to the vertices of this graph. So I and j are vertices of the graph. And if ij is an edge, you know what a graph is, right? A graph is given by a set of vertices and a set of edges. And every edge is a tuple of vertices, or an unordered tuple if it's an indirected edge, which is our case here. All right, so every so-called Ising variable is placed on a vertex, and it can take two values, 1 or -1. And this Ising interaction takes the form of the product of such Ising variables, so that it is 1 if both are the same, both are +1 or both are -1, and it's -1 if they are different. It's some sort of a parity interaction. There are other ways of assigning interaction structures to graphs. That's called an edge model. There are also vertex models, lattice gauge theories, and other things. But this is the most common one, okay? And then sometimes there's this coupling. Coupling is just a constant, Jij here, typically taken from the reals. I'm not fine with the reals, but physicists always take the reals because they generally require an infinite description. Actually, physicists take the reals, but they actually mean some sort of a subset of the reals which admits a finite description. But anyway, take them to be the rationals or the integers. That will suffice for our purposes. And often there's a minus sign in front. So if this coupling Jij is positive, you want to minimize the energy. That's a usual way of proceeding for physicists. Then you're trying to find configurations where spins are aligned, like neighboring spins are aligned. And it was introduced as a toy model for magnetism by Lenz, I believe, not really by Ising, but anyway, in 25, I believe, so nearly 100 years ago, as an extremely stripped-off model of a solid, like only modeling the spin of the outermost electron of a certain condensed matter system. And this interaction is supposed to be, I guess, some exchange interaction or something. But in the meanwhile, its importance extends way beyond magnetism because it is used as a toy model for many other complex systems. For instance, so the idea is that there are many systems which admit this kind of description, classical variables and a function on them that you'd like to minimize, say. I mean, the task is not always the same, but yeah. Say a gas. There's something called a lattice gas model, where you can discretize a volume, and every cell can be occupied or unoccupied. That's a binary variable that you can describe with an Ising variable. And then you can argue somehow that the Ising interaction is the relevant one, say. Or for artificial neural networks, they started with Hopfield, where variables are like Ising variables. I mean, there's some sort of an activation function. And the interaction between, like, along an edge is an Ising interaction. And you may be interested in different questions, such as learning, like how to update the couplings of what I would call the Ising model, so that the resulting function on the visible unit or so is your desired one. The questions may vary, but the underlying model is this one. Or in knot theory, there's something called Jones polynomial, which is an invariant of knots, like in one way only, in one direction only. And it equals the partition function of the Potts model, which is a generalization of the Ising model, in a certain parameter regime. Yeah, or in protein folding, the idea there is that the amino acids are at a given position are a classical variable, 21, like 20 for the amino acids plus 1 if you want to model the absence of them. And typically you want to try to describe some three-dimensional structure, and people have been using the Potts model for that, which is a generalization of the Ising model. I guess artificial intelligence models now are better than any kind of human proposal, but that's another story. Or in ecology, there's a wonderful book by Ricard Soule and Brian Goodwin called Signs of Life, where they explain how many different processes in life are like at criticality. They call this life at the edge of chaos. And at criticality in particular is the Ising model at criticality. This ranges from jungle, like trees in the jungle, to the mutation rate of viruses, to many other things. It's really cool. Yeah, or there's a recent paper on random language models, which also uses the Ising model, and at criticality again, and so on. I think also the US Supreme Court has been modeled somehow as an Ising model. I guess that the Ising variable there is whether the judge is Republican or Democrat, and yeah, I don't know how successful that is, but it's quite amusing. Anyway, so why? Why are they so expressive? Why can you do so much with so little? I don't know. But maybe it is because they are universal in some sense. Like simple such things are very expressive, as in they can explore all complexity in their domain. Here the domain is the domain of spin model physics. Maybe that's why such simple models suffice to describe so many phenomena. So I'd like to share with you this universality result. So let me first distinguish between two cases. So first of all, a spin system is a function from a given number of spins to energies. This very broad definition suffices for what I'm about to explain. The crucial point here is that the domain is finite. Okay, so it's like defined on a given system size. Whereas a spin model is a family of spin systems, an infinite family typically. For instance, a 2D Ising model with fields within homogeneous couplings and fields would be the set of all Hamiltonians of this form, we would have a sum over pairwise couplings with some coupling strength Jij plus a local magnetic field, a sum over HI/SI. Little hi is the local magnetic field. And here I'm able to, so here I can vary overall coupling strengths and magnetic fields in some set that whose elements admit a finite description, such as the rationals, and where VE, so the graph VE, is a 2D lattice, so it's a 2D grid with n nodes, but now for any n, okay? So a 2D grid of any size. And so such family, I will denote such a family by the set H sub alpha, and alpha will be an element of an index set capital I. Typically, this index set will be infinite. And this single alpha will capture all of these parameters that I've fixed, system size and coupling strengths, okay? The relation between spin models or systems that is relevant for this notion of universality is the following. Remember that previously for Turing machines we talked about the relation of simulation, right? Remember I explained how universal Turing machines can run any algorithm or can simulate any algorithm. This one looks a bit different. It's also called simulation, but it's a bit different. So first of all, at the high level, it's also a notion of mimicking the behavior. So in particular, we will say that a spin model simulates a spin system, H prime, if there is an element of the spin model, H alpha, that mimics the behavior of H prime, which means something like the fact that there should be some sort of a threshold, so that below that threshold, like an energy threshold, so that below that threshold, the energy levels, the energies, are the same as those of the spin system. And there's also some correspondence between the spin configurations. Everything's classical here, right? So eigenstate is the same as spin configuration. So the details are not so important. Maybe they are important if you try to understand what's the relation to Turing machines, which I don't. And so I'm trying to, that's why I need to show all these details, because I cannot simplify them. All right, so a spin model simulates a spin system H prime if for any threshold delta, there's an element of my spin model, so that for energies below delta, 4 things happen. First, the energies of H alpha and H prime are equal. Okay, this sentence is missing a verb and the attribute are equal. They coincide up to constant multiplicity, potentially. That means that for every level here, there might be m levels here, but this m is independent of the level. The states of a subset of the spins of H alpha, the so-called physical spins, are in one-to-one correspondence with the states of H prime. The partition functions coincide up to a constant factor and an error. So there's some sort of a constant factor gamma, pretty ugly I should say, but anyway. And some sort of an error term that goes down with delta exponentially. And the description of H alpha is polynomially larger than the description of H prime. Okay, I'm almost sorry to bother you with these details. As far as I'm concerned, for the rest of the talk, you can forget this and keep the idea in mind that this notion of simulation is a notion of mimicking, behaving like. More particularly, the notion of behaving like in the low energy sector. We're saying that the low energy sector of H alpha is the same, in some sense, as the full energy sector of H prime. Okay. Also note that the statement says a spin model simulates a spin system. Remember, this had a finite domain, and this is a family, right? And then universality is, you just need to yeah, it just says a spin model is universal if it can simulate any spin system. So you quantify overall spin systems, and you ask the universal thing to be in that relation with respect to all spin systems. Now, a spin model is universal if and only if the ground state energy problem, which I will define in a second, admits a polynomial time faithful reduction from SAT. I will define this in a second because I think these concepts are useful, are like basic concepts in computational complexity, which I think it's nice if you're exposed to them at some point. And it's closed, which I will define in a second too. All right. First of all, the ground state energy problem of a spin model the problem is the following question, if you want, but the language to that problem is the set of yes instances to that question, right? It's the set of yes answers to that question. That's usually how these things are defined. So it's the set of yes instances. An instance, remember, is a string X in the language. I mean, it is a yes instance if it is in the language. It's a no instance if it's not in the language, okay? To the question, given an element of this spin model, namely an alpha in I, and a k, that k is going to be a threshold, that should be something that admits a finite description again, say from the rationals, does H alpha have a spin configuration with energy below k? This is a yes or no question, so this is a so-called decision problem. And okay, what's important to know about this decision problem is that it is in NP. NP is the class of problems that can be solved in polynomial time by a non-deterministic Turing machine. Okay. And earlier I mentioned the big conjecture that P not equal NP. Everyone believes that the capabilities of a non-deterministic Turing machine in polynomial time are truly larger than the capabilities of a deterministic Turing machine in polynomial time. And then there's a notion of completeness within the class. I will come back to completeness within a complexity class in a second. But the most standard NP-complete problem is SAT. Have you heard of SAT? So SAT is the following problem, SAT for satisfiability. Given a Boolean formula, does it have a satisfying assignment? So this is a yes or no question. It's again a decision problem. If yes, then the witness for that fact is the satisfying assignment. If no, there is no witness for that fact. What is the witness? Well, that's how this class NP is defined. Yeah, so that's the definition of NP. Yes instances have a witness that's easy to check. It's a bit of a counterintuitive definition, but that's how this is done. One more bit. The witness is, in essence, the path that the non-deterministic machine follows during its computation. Remember that a non-deterministic machine can apply non-deterministic rules at every step, which means that at one step it can branch into different states and overwritings of the tape. And it can do so repeatedly, right? The witness is essentially the path that the machine will follow, or the path if the machine accepts. Okay. Anyway, so a reduction from SAT to ground state energy problem is faithful. Okay, sorry, just a second again. The ground state energy problem is naturally in NP because the witness is the ground state configuration, or it is the configuration of spins whose energy is below k. If you plug it into your Hamiltonian, you can easily check that its energy is below k. What's interesting is that for some simple models, like the 3D Ising model without fields or the 2D Ising model with fields, it is NP-complete. So it's as hard as it gets for NP. And this was shown by Barahona in '82. And this implied that finding an efficient solution for the 3D Ising model amounts to proving that P equals NP, which no one expects. And so I used to give a course on computational complexity for physicists, and that's one of my justifications of why computational complexity is useful for physicists. Well, in this case, it told everyone that this efficient solution of the 3D Ising model that they had been looking for 40 years cannot exist unless there's a massive collapse, completely unexpected in this world of computational complexity. All right, but in particular, such a reduction is faithful if the witnesses are also preserved. So if there's a map that maps yes instances of SAT to yes, witnesses of SAT to witnesses of GSE. Most reductions are constructive, and so they map witnesses as well. Okay, and then we say that the model is closed if for any two elements in the model, you can add them up, and you can simulate the result of that addition by a third element in the model. Some sort of modularity condition in that family. And simulation was defined in the previous slide. Okay, and then the 2D Ising model with fields within homogeneous couplings is universal, and so is any more complicated model. So in plain words, essentially every spin model is universal. And the interesting direction is the one that says that these two conditions suffice. And well, what goes on essentially in the proof, I have left it as a slide in the appendix in case you want to check it out, like in plain words, the main steps of the proof. What goes on is that SAT, like this reduction from SAT allows to encode computation in the ground state energy problem of the model. And but that is not enough for universality because that would only allow you to simulate the lowest energy. So for universality, you additionally need closure, which lets you add up all these contributions in a way that they don't mess each other, like they don't cancel the other's contribution or so. Yeah, so you can add them up and finally have a nicely behaved low energy sector of this universal spin model so that is mimicking the behavior of H prime, the spin system it is simulating. I'm going to try to understand, so I'm trying to understand what's going on here. And I don't really know yet. Is this exclusive to spin models? I don't know, but I wouldn't expect so because they are just functions. They are families of functions. So I don't know, is this some veiled form of Turing universality? There are some similarities, but it doesn't seem to be the same thing. I'll go there in a second. Or is it something else, like maybe the basis of a vector space together with some sort of a denseness argument? Perhaps. Okay, so I believe that understanding these questions is worth it, is beneficial, because we will be able to transfer different, like, universality results among different fields. So let me point out the similarities. So for a spin model, this can be, if it's defined, say, on a hypergraph like that one, it can be transformed on a universal model by adding auxiliary spins. These are my gray spins here. Okay. And where I have actual and auxiliary variables called physical and auxiliary spins. And the auxiliary variables are additional degrees of freedom, are like my extended domain of the function, which, when fixed, tells the universal model how it is supposed to behave. In this case, it tells the 2D Ising with field, say, like what other spin system it is supposed to behave, like which spin system it is supposed to mimic. Okay. For Turing machines this morning, we saw that the same was the case. A universal Turing machine was fed an enlarged input, part of which was used to specify the target Turing machine it's supposed to mimic. And there's a similar notion for feed-forward neural networks, where, and also for restricted Boltzmann machines. So for a feed-forward neural network, the goal is to learn or represent a certain function from a certain nice set, like a continuous function. And the idea is to add lots of so-called hidden units so that whose parameters will contain a description of that f, of that function. And yeah, so that the visible units mimic f, the target function. Okay. But how deep are these connections? I don't know. So I want to prove theorems. And to that end, I'd like to understand the reach of universality and also that of undecidability, which implies also understanding the connection between the two. And well, I propose to do so in the following way. On the one hand, by coming up with a framework for universality. This is like a top-down approach. And on the other hand, by comparing two examples, that's like a bottom-up approach, namely that of Turing machines and spin models. And somewhere in the middle, I'll explain the relation from universality to undecidability in a more general way than the way I explained it this morning. All right, so this framework necessitates two parts, as far as I can see. A conceptual part and a categorical part. So categorical is a way of saying formal. It could be done differently, but we've tried to do it. We're trying to do it in a categorical way. So, okay, so conceptually. This starts with the question of what does universal mean? I believe that at a primitive level, it means relative to the universe. And by extension, it means all-encompassing. So the second is a frozen metaphor for relative to the universe. And most of our uses of universal are frozen metaphors. So universal as all-encompassing means the following. So kind of embodies the following basic structure. Given a collection, C, and a relation R that lands in C, lands just means that the second element of the relation is in C, but the first need not be. U is universal if U is in that relation for every element in C. It's a very basic structure. So I'm not asking the collection to be finite. I'm not asking U to be in the collection. I'm not asking the relation to be transitive. I'm barely asking for anything. I mean, it's very basic. But we believe that that captures the minimal structure of universality. Yeah?
So in the previous slide, what precisely is U an element of? And is it universal in C, or is it universal in which context?
It's universal with respect to that collection and that relation. So the definition says, given a collection and a relation, something has a property called universality if it satisfies what's written on the right. And generally, I don't want to require U to be in the set. I think somehow the interesting kinds of universality require U to be in the set in some sense, but in general, it need not be in the set. I don't want to specify what it's an element of. So this is instantiated in many cases, okay? So remember, we're doing this kind of top-down approach. So we're trying to cast a very kind of broad net and see how many cases we can fish somehow. Universal Turing machine. Well, of course, C is the collection of Turing machines, R is simulation, and U is a universal Turing machine. But also completeness in a complexity class. like what I said earlier, that SAT is NP-complete. C is the collection of problems in that class. R is some sort of a nuanced reduction. It could be like a polytime reduction or just a computable reduction if you're talking about recursively enumerable completeness. And U is a complete problem. A universal gate set for classical computation. C is the collection of Boolean variables. The relation says that there exists a gate, a sequence of gates from U whose result equals C, and U is the universal gate set. Or for quantum computation. C is the set of unitaries of any size, and the relation expresses that for every epsilon there is a sequence of gates of U which is epsilon close to C. It's a bit different, this relation, and U is a universal gate set. Or universality classes of spin models. I don't know if you've heard about that, but so spin models, when close to criticality, behave similarly, many of them, and they can be classified into various families called universality classes. This was a result from the 70s by Wilson and others, very important and very beautiful. And so in that case, C is the collection of all spin Hamiltonians. The relation says that C flows under some renormalization to U. And U is the collection of fixed points. Okay, that's another way of expressing what I just said, that there's a simplified description around criticality, which is just capturing typically the so-called critical exponents, which suffices to describe very many spin models. There's also a notion of quantum spin models. So the classical and the quantum version, in both cases, C is a collection of classical or quantum spin systems, R is a relation of simulation, and U is a quantum universal spin model. For feed-forward neural networks, we would have what I mentioned earlier. C would be the set of continuous function. The relation expresses that for any epsilon, there is an element in U, meaning a choice of weights and biases, so that the function in the visible units is epsilon close to C. And then U is this kind of family, right? It's the set of feed-forward neural networks with one hidden layer of unfixed size and weights. And similarly for restricted Boltzmann machines, where C would be the set of discrete probability functions over a certain size, R is a similar relation to above. So for any precision, there's an element in my family that can approximate that's epsilon close for some notion of distance to my target model. And U is the set of RBMs of unfixed weights and unfixed internal size. But also in math, the basis of a vector space has this property. C is a vector space, namely all points in there. The relation is linear combination, right? So it says that there is a linear combination of the elements of U, which equals C. And U, we say that U is universal if it contains a basis, if it's a generating set. Or the extremal point of a convex set, which play a similar role to the basis vectors of a vector space. So in this case, C is the convex set. It could also be a convex cone, and then you would have like rays, extremal rays. But for a convex set, the relation expresses convex combination, and U is universal if it contains a set of extremal points. Also, the universal graph sees the set of graphs of any size. The relation expresses minor. There are various notions of minors. And this is literally the definition of a universal graph. Or a universal differential equation, where C is the set of continuous functions, and the relation says that for so this universal differential equation has a solution set which is dense in the set of all possible continuous functions. So for any epsilon, there's a solution of U, which is epsilon close to C. Okay, or in, maybe you may have heard of the universal grammar. It is some sort of a meta grammar because it has unfixed parameters. so that if you fix these parameters, it becomes the grammar of any natural language in the world. Natural language, remember, is languages that we speak. So I'm talking about the grammars of languages that people speak. That's still the easier part than talking about the semantics of these languages. And so I think this was proposed by Chomsky. All I'm saying here, not endorsing or not endorsing, all I'm saying is that the structure is instantiate our basic structure of universality, because our basic structure is so bare that it's more or less instantiated in many cases. So C would be the collection of all grammars of natural languages. The relation expresses that there is a choice of the parameters of U so that it becomes C. Typically, there are very few parameters, like, I don't know, 15 or something. And U is the universal grammar. Or in the problem of universals in philosophy, which is, it's hard and kind of painful to simplify in philosophy. Maybe it's really difficult. But it asks something like, how can we assign the same attribute to different particulars? Because it seems that the relation between different particulars is not of this world. And so there are two main camps. Some are called metaphysical realists. That starts with Plato and Aristotle, although I don't want to claim that what I'm going to say is what they said, because I guess that is disputed too. But that's what I've learned from introductions to metaphysics. Well, they claim that shared attributes are due to their joint instantiation of one common universal, or called a form, I think, in some cases. And that, like the universal of redness, or of roundness, or of being virtuous, or whatever. And I guess some would argue that these universals live in another world, not the physical world, but I guess that's also disputed. Anyway, and then there are some other people, starting with Occam and others, who say that there are no such universals, and then they have many problems. So again, yeah, the universal of redness is in the relation that we're talking about with respect to all red objects in the world. What's interesting is that one of the critiques to these metaphysical realists is that if they take the attribute is non-self-instantiating, which is another incarnation of the liar paradox, they of course run into problems because it is self-instantiating if and only if it is not self-instantiating. Yeah, that's one of the challenges that they face. So I would argue that the tension between universality and undecidability that we understand well for computation and that we understand not so well for other cases is present already, yeah, in the problem of universals in metaphysics, at least in an aspect of this problem. And why do we do that? So that we can ask questions about these different instantiations. For instance, we can ask which of these onsets the generation of complexity. Well, I would say that universal Turing machines do, universal spin models do as well, but universal grammar does not, and the problem of universals does not either. Maybe these are like these minimal descriptions or bits that Matt Leafer was talking about today. They don't really kind of cut the things in half, but they are questions that kind of let you cut through and distinguish interesting from non-interesting types of universality somehow. This is something like the jump to universality. If you've read David Deutsch's book, The Beginning of Infinity, I'd like to make this precise, but I'm trying, I'm not sure. Which is related to undecidability. Again, that's another interesting criterion. Turing machines are, the problem of universal seems to be, but universal grammar, the basis of a vector space or extremal points, seem not to be. Okay, so with that, I'd like to say a few words about the categorical framework. But Sebastian and Toby, who are here, have a nice poster about it. So, okay, that's a little abstract. But so we try to set up a categorical framework as follows. So we have our central object is something called a simulator, which is a map of the form. So, okay, so this P and C and T and so on are like objects in a category with, which has a certain structure. And so a simulator is a map of the form, so from programs and context to things and context. And in the middle, it has this form of a map called ST, which is called a compiler, and SC, which is called a context reduction. The names are not important. And later on, there is a further map to behaviors, which would be something like energies or the output of a Turing machine, and so on. And here we can provide a more nuanced definition of universality than the one I provided earlier in the conceptual framework. So we would say something like, a simulator is universal if for everything there is a program P such that for any context, the evaluation of SPC equals that of TC. So so for anything, there's a program that you can fit to it, which will make it behave like it, mimic. And what does mimic mean? Mimic means behave similarly kind of in all contexts after going through the evaluation. I believe the details are not so important. What's important is that our central examples, the spin model and the Turing machines, both fit in there. And I would explain this if I had time, but I've left the slides in the end, like in the appendix. I guess you have the slides. They're universal in this sense, but also things you wouldn't expect, or maybe you would expect, but that in any case are not called universal, like a dense subset. In a dense, like if the rationals are dense in the reals, the program to reach a given real is the rational and the precision that lets you get kind of close to that real. This is the idea of how being dense in a set is also a form of universality, at least here. It's also in the extra slides. And so the framework allows us to relate universalities and kind of grade them, which is what we wanted to do. Okay, and maybe that's the last kind of difficult slide. After that, it will be easier. So mathematically, universality may be some form of surjectivity in the following way. Okay, so take a function with a domain f cross b to c. Now, say that it is weakly point surjective. It doesn't matter. The word doesn't matter. It's some weakly point surjective. If for any function g from b to c, there is an a in the capital A, so this extended domain of the first function, so that when you fix it, f of a behaves like g. So f of a is equal to g on all elements of b. Okay? So f has an advantage. It has a larger domain. So, and you say that it's weakly point surjective if it can represent any g. And represent means that there exists an element of this extended domain so that they behave the same. And then there's this theorem, and in category theory, Learnir's theorem that says, let f from a cross a to b be weakly point surjective, then every g has a fixed point. Okay, so this is usually stated in the contrapositive, where you say, if you have a function without a fixed point, like negation, negation flips 0 to 1 and 1 to 0, so it doesn't have a fixed point, then f cannot be weakly point surjective. Namely, it must be leaving some functions out. Some functions cannot be represented by f. And this tension, I think, is the tension between universality and undecidability. So this being weakly point surjective is something like universality, something like capturing every function from B to C by fixing an element of my extended domain. And this Learnir's theorem, I think, is expressing the limitations of, the proof is by self-reference and negation, of course. Okay. Having a fixed point is like saying that if I say I am honest, that's all right. I'm doing self-reference, but that's not a paradox. The problem is when I say I'm a liar or I am not honest. That's what this is expressing somehow. And Well, in particular, we see that for linear bounded automata, remember I mentioned earlier that they were not universal? Well, then they are not subject to this Learnir theorem. But for Turing machines, they are universal, and so they are subject to this Learnir theorem. So that's the kind of things we're trying to understand in order to try to clarify or shed light on the relation between some sort of universality and undecidability. Okay, that's going to get a lot easier now. Sorry if it was a little technical. Okay, so just give me 5 more minutes. So broadly speaking, remember we had undecidability this morning. Well, I want to understand it in a broader sense. I want to understand it as a statement that no system can thoroughly talk about itself. And I'm going to explain again what I explained in the morning, maybe from a different perspective. Instead of system, take a set. And talk means describe an attribute. Remember attributes? Function from the set to 0, 1. And we identify the attribute with its extension, the set of elements where it is true, which is an element of the power set. For example, for this finite set with 3 elements, the power set has 8 elements. And that element of the power set is the attribute different from B, for example. But by Cantor's theorem, a set can never be put in one-to-one correspondence with its power set. More precisely, there can never be a surjection from a set to its power set. Proven by, you remember that diagonalization argument? Diagonalization is self-reference. Flipping the diagonal is negation. The liar paradox. So it's another way of saying is that wherever you are, in whatever system you are, if you want to determine the truth value of the sentence, I am a liar, you cannot do so with the power of that system. The liar paradox is outside the system. To analyze its truth, you need tools which are outside the system. For whatever system you have, no matter how super powerful it is. This is very powerful. I recommend, there's an entry on the Stanford Encyclopedia of Philosophy called Self-Reference. It's wonderful. And you can see how this sentence is false, the halting problem, Gödel's first incompleteness theorem, Russell's paradox on set theory, Tarski's theorem on the undefinability of truth. Many of these things are, at its core, the liar paradox. And so it limits what can be formalized, what can be computed, what can be known, what can be said to be true, what can be said to exist. There's also some people in philosophy, like the anti-realists, which take these liar paradoxes in order to challenge a theory of truth, and so on. So it's really powerful and it's very robust. It can be incarnated in many different systems. And it's very far-reaching. It's very resilient because you cannot fix it in a finite way because, of course, it says for any set, this is the case. So, yeah. For example, it implies that there are infinitely many types of infinity. It can be made precise by Learnir's theorem. Okay, so intuitively, universality allows for self-reference, which is a step away from self-reference and negation, which is at the core of undecidability. But the precise notion will depend on the type of universality we want to capture. So that's why I couldn't get to this intuitive argument before going through the conceptual framework for universality. And I see some tension here. There's a tension between universality trying to capsize the complexity of the system and undecidability saying that is impossible, that will never thoroughly work. Okay, I think I don't have time for that. Lydia? Okay. All right. Well, I'll be brief. Okay, the second approach, remember, was to compare two examples. That's a lot easier. So in particular, we want to compare spin models and formal languages. And to this end, we have cast spin models as languages, as formal languages, which is sort of the same as saying as the automata that recognize those languages. I mean, technically, we have cast them as languages. And I won't go into how we've done that, but I just want to emphasize the the results. Remember that we had formal languages here. This was the Chomsky hierarchy, and these were the automata that recognized these languages. What we see is that so the language of a 1D spin model corresponds to, is a deterministic context-free language of an effectively 0D spin model is regular, and of 2D or higher D spin models is context sensitive. Okay, so perhaps these distinctions are at this point not so important. What is important is the conclusion that, for the purposes of this talk, what's important is the conclusion that the language of any spin model has a grammar. And remember that grammar, how I like grammars, that they were like a mold that allow you to generate an infinite set. And so a spin model has some sort of a local structure. It admits some sort, so that infinite set has some sort of a finite structure. I guess this is a precise way of expressing the idea that some aspects of nature are describable, like admit a finite description. I think that's a way of saying this for spin models. The second thing we realize is that on this side, on the context-sensitive side, we have universal spin models, but on the other side, universal machines only happen for recursively enumerable languages. So there's some sort of a mismatch of universality, which we don't understand yet, and it's kind of hinting at the fact that the universality notions are different. I could tell you more about that, but perhaps it's nicer if you just get an idea of the methods and the kind of questions we ask rather than the precise results we get. Okay, so we've been trying to understand what is the reach of universality via a conceptual and a categorical framework. The conceptual framework captured the idea of universal as all-encompassing. Encompass is the relation R, and all quantifies over all elements of a collection. And in the second approach, which is complementary, we kind of had simulators. And the bottom-up approach says that let's compare the two examples we understand best, spin models and machines. And well, we find that, yeah, the languages of every spin model has a grammar, but not the most general type of grammar. For you, if you're interested in that, there are so many things to do. Quantum, at the quantum level, yeah, I don't think undecidability, so quantum is not going to make a difference for undecidability, but it might make a difference for universality. And there are quantum versions of several of these types of universality that I've been talking about. What's more unclear is whether a statement can be made about universality for language or for thought, something that involves semantics. That seems to be quite muddy indeed. I used to try to understand this jump to universality as a perspective to understand the origin of complexity. I try to share these ideas in a TEDx talk. It's very short, so perhaps you find it entertaining. And well, if you like undecidability, I can recommend this book, particularly Logic Comics. It's a graphic novel. It's great fun about the struggles of mathematics at the beginning of the 20th century. GEV is the classic. It's not very clear, I should add, but it's very fascinating. And the outer limits of reason is very clear on Cantor. And on the brink of paradox is super clear. We're using it for our course on paradoxes. They are all very accessible and like great fun. Yeah, maybe. And I want to end with a provocation. What happens with the brain? Does the brain we seem to understand these paradoxes. Why so? And why can a computer not do it? And what happens with art also? Art seems not to be bound by these limitations of undecidability. And these are the group. I'd like to thank them, particularly Sebastian and Toby, who are here, and we have open PhD and postdoc positions. Thanks. Mm-hmm. Yep. Sorry, I ran over time.
No, I'm just wondering, in this presentation of this fixed theorem, you have the assumption that this category has retractation closure, right?
Mm-hmm.
So I'm thinking of, if you are relating precisely this obstruction to having functions, like for instance the negation, that it doesn't have a fixed point, that this implies somehow that you are like in this region of paradoxes. I was thinking of if there's a way to tailor these categories like free of paradoxes somehow, in the sense that you restrict, and maybe if you allow all your possible morphisms in this category, then you are also allowing these morphisms that doesn't have fixed points. But I'm saying, okay, maybe I can restrict my category, I can restrict to this place when I will only have these fixed points, so I'm not perceiving, or my category is not seeing these paradoxes out of the Learnir theorem, not having these weakly surjective functions. Like there's a way to tailor those things, or describing these universes somehow.
So let me rephrase your question in a broader way of how can you fix the liar paradox? And can you try to avoid the paradox of self-reference and negation by not allowing for negation, for example? Well, if you don't allow for negation, then you lose expressivity. And if you want to allow for negation in a controlled way so that it doesn't generate the paradox, then what people have done is to generate a hierarchy of levels so that every level can only refer to the previous one, so that it avoids self-reference. But then typically it only recovers the full expressivity in the limit. And I think a limit is not a physical thing. So I guess that's not a satisfactory solution. But of course, many people have thought about that for centuries or even millennia. It's not exclusive to, let's say, category theory. In plain words, what happens is that whenever you have the basic ingredients to do self-reference and negation, which are very basic indeed, then you're doomed, I want to say, or you're done, or I don't know, maybe you can take it in a positive way, and you're bound to this argument. There will be a sentence whose truth or that will not be analyzable from the tools of the system, and it's not a single sentence, but in fact it's most of the sentences.